Welcome to Talk 5. In the last talk, again, we talked about the identification of the two extra dimensions of time. You remember using the Trinitarian equation, this is what I call it, and we'll see it quite a lot in the talks to come. We identified time as being three-dimensional in our universe, with the extra terms we identified as the past and the future. Before I move on from time, I would just mention that the thought of a three-dimensional time is not new. Thomas Aquinas in the past called these various times, obviously this is tempus, he called the minus t equivalent evum, and the third term, which we call the future, he called eternitas. Now we've no idea how Thomas Aquinas arrived at this conclusion, but I thought it was just worth mentioning that what I'm proposing here is not totally new. The one thing I did say about the end of the talk was that I couldn't, although I could identify two dimensions for time, I couldn't do it for space. But help might be at hand from a completely unusual source: quantum theory. Let me show you what I mean by referring to the two-slit experiment, the twin-slit experiment. Einstein didn't like quantum theory. He didn't like this idea of two particles being at different places at the particle being in two different places at the same time. But because of twin-slit experiment, which was reproducible, he really had no choice. But he forever, right to the end, remained sceptical about this theory. And so I want to give you another take on it. The experiment basically is that if you fire a particle, electrons or photons, at two slits in a sheet, then what should happen is particles pass through one of them, and there should be a single line shown on the screen to collect the beams. Could be a negative photographic plate or whatever. But what they found was that when they shone a particle stream through the two slits, an interference pattern arrived. The only explanation was that the particles were simultaneously going through each slit. Now I'm just wondering if this is the total truth, whether we cannot identify this somehow differently. If we imagine, and to take my theory, that a photon, say, a capital P, a perceived photon, is made up of three dimensions. This is the photon that we can identify with, an unreal photon and an imaginary photon. By using the same notation as we've done previously, and you must be becoming familiar with now, we can say that the perceived photon is indeed a plus or minus photon, a real and an unreal photon. So instead of being one particle hitting this twin slit, in fact there is a particle and its almost negative other one, the unreal one. Could it be that in this experiment, instead of the real particle only going through here, both particles pass through here? You'll no need then to go to this particle-wave duality to explain things. Because what happens, well, you can say, well, hang on, the unreal photon, how can we see it? How does it come from? But funnily enough, I understand, and believe you me, I'm not an expert in this field, but these images that are produced on the back all depend on something called the probability amplitude. And the thing about the probability amplitude is it is the square of a value, energy, luminescence, I don't know. But of course we all know that when you introduce the square of an unreal particle, we get a real particle. This is the beauty of the mathematics that we're talking about, the mathematics of the square root of minus 1, I. So could it be that this is the explanation? Much easier, much simpler than the particle wave duality. And could it be that Einstein was right all along to be sceptical. There's another aspect of the quantum theory that we might consider here at this point. It's something that moves us from the scientific almost to the spiritual side of things, and I want to show how this Trinitarian equation that we've seen so often comes to play a part. I'm talking, of course, about Schrödinger's cat. Now, the Schrödinger cat experiment is a thought experiment. No real cats are injured in the course of this experiment. But Schrödinger imagined that a box, and in the box, a sealed box, a cat, a vial of poison, some sort of trigger mechanism which gave rise to, which was activated by a radioactive substance that at random emitted some radioactivity. The radioactivity produced a alpha, beta or gamma, whatever, particle. It broke the vial of poison and the cat died. Now after he sealed the box, or after in the experiment we sealed the box, and because the trigger acted at random, at any time one had no clear idea of whether the cat was alive or dead. In fact, it was impossible to determine whether which state the cat was in until one actually opened the lid. And this led to Schrödinger to imagining that the observer played an integral part in the experiment and played a part in future quantum theories. And I wonder whether there is a simpler answer to it. If we now call the mortality of the cat, capital M, perceived mortality, and again we write it in terms of our Trinitarian equation, real mortality, unreal mortality, imaginary mortality, we can follow the same notation and come to the conclusion that the perceived mortality is indeed plus or minus M. In other words, the cat can be alive and dead at the same time. Okay, no need for quantum theory. Now we're going to go on and talk about other aspects of the Trinitarian equation and how it impinges on our life in this, in human lives in this way. And we will do it with reference to the inevitable traits of man: love, courage, altruism. And we'll talk about that in our next talk. Talk 6 is all about black holes and dark matter.